So ideally, if you're gonna give me an answer, it should be something with length, right? So meters, right? Because that's what our units show. If you had said seconds, that wouldn't make sense, right? Because we're talking about wavelength. And it's also asking for it in meters. And this corresponds to answer choice E. So again, we need to realize, it tells us what, we should know what equation to use based on just reading the question, right? The de Broglie wavelength, that tells me I need to use this equation. All right. So this answer, we're gonna do number 11, and answer choice C is something that they don't go by anymore. This is just called the angular momentum quantum. And I'll give you all just a minute for this one, okay?
Like now, but for in the future, you might tell you that you want France and but expect this. Okay, too, not really open. I would just bring it.
Raise your hand if you got an answer. Perfect. Raise your hand if it's the right answer. Be confident. If you have an answer, be confident that it's the right one. And that this the wrong one.
Might as well be confident.
Exactly. Maria, you got an answer? Nice, nice.
It's E.
Wait, how do you know?
Bro, I know everything.
For sure. Sounds about right. Okay, so all the orbitals in a given electron shell, and it abbreviates or it says energy level, have the same value of what quantum number? And what did we come to an agreement on? What do you say? Okay, did you have an answer? Yes. It is principal. Do you know why? Yeah, so anything, so let's just think of a random number, n equals 4. You already went to the 4th energy level, right? So anything after this is talking about an orbital in the 4th energy level. So if it's saying all the orbitals in a given electron shell energy level have the same what? All the orbitals may not have the same angular momentum, right? Quantum number, because you can, when n is equal to 4, you can have an n value of, or L value of 0, which corresponds to our s orbital, and it would also have 1, which would be a p orbital, right? Or you can have a 3 or 2, which would be a d orbital. So each of these have a d orbital looks different than a p orbital, which looks different than an s orbital, right? So they're not the same orbital, but they're all in the same energy levels, right? So every, like the 4th energy has an s orbital, it has a p subshell which has 3 orbitals, has a d subshell which has 5 orbitals, and then it has an f subshell which has 7 orbitals. But all those orbitals are in the 4th energy level. Okay. So next question is asking, all the orbitals in the energy level have the same what quantum number? They for sure have the same principal quantum number because they're in the same energy level, right? It literally tells us that right here. But they may not have the same L angular momentum quantum number, right? Because they could be 0, 1, 2, right? Does that make sense?
What is, what out of like the NP and all of that, what does energy level represent again?
So energy level is just, if you look at the periodic table, energy level would be the row, or the period, I guess is the correct term. But it's basically saying like the first energy level just corresponds to the 1s subshell in a hydrogen atom, right? Or anything has a 1s subshell, right? Even let's just pull up the periodic table here. Even calcium has a 1s subshell, right? It's just looks a little different. Oh wait, yes, yeah, it just has a really big dense electron cloud that also has a 2s, a 3s, and a 3p. Or not 3s, 4s. So what the n value is just talking about the energy level at which the electrons reside on, okay? So you can have it in the first shell, second shell, third shell, fourth shell, etc. Yeah, Maria.
So today, Dr. Armon asked us a question and it was like, what is the highest energy orbital a hydrogen atom can be at? Is it 3s and 3p? Is that what the answer is?
The highest energy level.
It was 3s and 3d. Yeah, that's what he asked. I didn't understand. I put whichever one was.
So was it multiple choice?
It was select all of five.
So, wait, hydrogen atom.
That hydrogen.
I know, it's confusing. It was a, no, I thought it was, no, it's not one S. Don't think of the Balmer series. Yeah, no.
I'm gonna have to see this.
It asks, what is the highest energy orbital a hydrogen
Do you have a
atom can be?
picture?
Yeah.
Yeah, that one was confusing, right?
Give us 1 second.
Sorry. It's the three.
She's.
So the question, I actually, I think that was wrong, but he said that, I don't know what this, the way I was considering, like, you think about and everything, right? Like the. Yeah, and like the. No.
It's like 3 of 3.
Yeah. I think the highest.
Okay, that's interesting.
How many?
You should email that to me. I'm gonna ask you.
It's the three words, D and E.
Okay. So it makes sense to everyone that the answer for 11 is B, yes or no? Yes. You wouldn't lie to me or Rich, right? I wouldn't lie to y'all. Yeah.
It's the L stand for magnetic. Like the wording for L, what is it?
Where did he send the what?
L is angular momentum.
So what is L?
That's the magnetic quantum number.
And then M such as?
And then spin quantum number. Okay, number 13 is the next one. There are blank possible values for the magnetic quantum number of an electron in a 5F subshell. And this kind of requires you to know your rules of quantum numbers and also which one is the magnetic quantum. So, yeah.
512.
Oh, because that one's horribly worded. It's really weird.
I didn't know.
And then the answer doesn't make sense.
Okay, to y'all's question about why the hydrogen atom's highest energy level can be 3s or 3d, I figured out the answer. So hydrogen has how many valence electrons? One. And yeah, what's the definition of an orbital?
Do you have to? Two, I can hold two electrons.
That can hold an electron.
It's a
Here we
function.
go, general.
Yeah, it's a what type of function?
A wave function.
It's a mathematical wave function that determines the probability of finding an electron in a given space.
Okay.
So, right, since an orbital is the probability of finding an electron in a certain place, hydrogen only has what? One valence electron, right? That means what? It can bond to pretty much anything. So if it can bond to pretty much anything, say for example, hydrogen were to bond to something like, I don't know, aluminum. Aluminum has a p subshell, right? So if that's the case, wouldn't you agree that hydrogen has a p orbital? Yeah.
Why does it stop at 3s?
Yeah.
Why can't it go 4s?
Because the only C options didn't have that. Otherwise, it'd be the
Options
highest.
had like 6s, you pick 6s.
Yeah, because the hydrogen atom has every single orbital there.
And that's only hydrogen.
The answer is 7.
Cat calling you.
Yeah, the answer is 7, Alex.
Be in any orbital?
Okay,
Be in any orbital.
so I'm gonna explain why it's 7, okay? So if in the 5F subshell, we can just go ahead and run through our quantum numbers. What must the principal quantum number be in the 5F subshell? 5, right? That makes sense because it's in the 5th energy level. L must be what?
So. Do you have periodic table?
I had 3 and 4. What did you say?
That is three.
Okay.
Three.
And the answer is 3. Is that what you said? Yeah, the answer is 3.
I should.
I heard someone say 4. Why is it not 4?
That's G.
Right? Because we know that L is equal to 0. This is S. 1 is P, 2 is D, and then 3 is F, and then 4 would be G. Okay, so So L must be 3, and then M sub L has possible values of negative L to positive L, right? So if we were to write all of them out, we can say M sub L can be -3, -2, -1, 0, 1, 2, 3.
So it has any.
And that is 1, 2, 3, 4, 5, 6, 7 different orbitals in the F subshell. Right, and it's asking their length possible value for the magnetic quantum number. So the magnetic quantum number is M sub L, there's 7 possible values for M sub L, therefore answer would be 7, right? And if it asked how many possible, what's the max number of orbitals in the F subshell, 5F subshell, you would say 7 as well, right? Because each of these M sub L values corresponds to a single orbital, right? Are they just communicating to themselves? I was any, wait, so if n equals 4, then L can equal, yeah, Michelle, L can be 0, 1, 2, or 3. But it has to be only one of them for a specific quantum number. They can't be all 4 at one time.
I mean, yeah.
Yes, yes,
You're looking at the valence electron.
okay. Oh, okay,
So.
Okay. Wait, isn't L is equal to n minus? Oh, yeah, so you're saying L, why, you're saying, isn't L equal to n minus 1? It can, the possible values for L are from 0 to n minus 1. It's not always going to be n minus 1. It's not always going to be 0. If n is equal to 5, it can go from 0 to 1, 2, 3, or 4. Okay. Makes sense? It could exactly perfect. Thank you. Okay. Any questions on number 13? Yeah, so the rule is L can be n, it can go from 0 to n minus 1. It can't be n, okay? So if n is 4, L cannot be 4. That would be violating the quantum number stuff, yeah. Okay. Number 14, I'll give y'all just a minute. Yeah.
It's the L.
Oh, yeah. As you, yeah, that's an old term they use for the angular momentum quantum number. They don't use that anymore. It's an old worksheet.
Yes. It's only possible, like,
Okay, what's the answer?
it's C.
This is an exciting.
So Maria already answered it, so I'm sure y'all heard her. But why can it not be, why is it C?
Yeah.
Well, the answer choices we can tell are all in the second energy level, right? So we know n must be 2. That tells us that L can be 0
And then.
or 1, right? 0 or 1, it's not both. The 0 corresponds to the what subshell? What's the, say it louder, guys. Perfect, and 1 corresponds to E, yeah, there we go. So now, if we have a possible 2S, we have a possible 2P. In order for it to be a 2D, we would need an L value of what? 2, but is that possible? No, because L can only be 0 to n minus 1. It can't be n, right? So C is impossible. Does it say that? It does not exist due to the constraints of angular momentum quantum, not the, yeah. Again, this is the same thing as angular to momentum.
It's not exactly.
No.
Any questions? No
Even
questions,
in.
perfect. What I'd like to see,
Because
okay,
it'd be like one.
let's see if you know your orbital geometry. Which orbital is spherically symmetric? S, right? That's a pretty easy question. But this one, these 3 quantum numbers correspond to a specific orbital because it's all the way down to the n sub L. And it's saying n equals 3, so 3rd energy level, L is equal to 1, that's our 3s, right? And there's only one possible S subshell. So we just said in the previous problem we did that S subshells are what? Spheres, right? So what would be the most likely structure? D, right?
And then,
Y'all think y'all are starting to get a hang of this now, or?
What's the number of points on
Perfect.
this particular?
Yeah, you got a question?
So I thought like in order to get the angular momentum, it was 3 minus 1 equals 2.
No, so it's n minus, so so give me a random number that's not greater than 5.
4.
Okay. Perfect. So if n is equal to 4, our L can go from 0, it can be 0 all the way to n minus 1. So not 3 minus 1, it's n minus 1. So it's 0, 1, and n's 4, right? So 4 minus 1 is 3. So L can be 0 all the way to 3.
Copper,
2, and then 3. It's only one of them at a time. You can't have more than one L value associated for each quantum. For each electron, right? So that would be saying that this electron is occupying 4 different subshells in one moment in time, which makes no sense, right? Because I mean, electrons don't make sense to begin with. Because it already says like they could be in one place, both more than one place at a single time, but this doesn't make sense. It doesn't help, you know, it doesn't make any more sense than electrons already do. Okay, perfect. Let's do 18. Give y'all just a minute, so.
If you could say.
I'll start all of it.
Who's lost? Raise your hand, I would try. No one's lost, or unless you're not telling me,
She's a very approachable person. I know.
that's good. Raise your hand if you have an answer. So I see a lot of people not raising their hand, but I also didn't see anyone raising their hands saying they're lost. So I'm okay. Can I pick on you? Yeah, okay.
Like, I made recommendations.
You're right. Wait, each. Yeah. Okay, so if you didn't know how to approach this, you can just say, what is the L value for p orbitals? 1, right? And m sub L, this will tell us how many orbitals there are. And why do I care about how many orbitals there are? Because each orbital can only hold a maximum of how many electrons? 2 electrons, right? And you know that because electrons can either have an upspin or a downspin. So each orbital can have 2 electrons. They must be opposite in spin. So if you add a 3rd electron in there, you can't have a +1/2, +1/2, -1/2. Right? It doesn't work like that. They would be repelling too much. So each orbital can hold 2 electrons. So if we figure out the amount of orbitals there are, we can figure out the amount of electrons. So m sub L can be -1, 0, and +1. How many orbitals is that? Remember, m sub L tells us how many possible orbitals there are. So -1 is the first orientation, 0 is the second, and then +1 would be our 3rd orientation of an orbital. So how many orbitals are there in a p subshell? Right? I think you said it, say it.
3.
3, exactly, right? So 3 orbitals in the p subshell. If each orbital, I'm gonna pick on you again. If each orbital can hold 2 electrons, and you got 3 orbitals, how many electrons can fit in there? 6, right? Let's change this question up a little bit. Say it was talking about the F subshell. Aside from memorizing that it can hold an X amount of electrons, how would you go about this? What must the L value be for an F subshell?
7.
Not quite, because remember, 0 is S, 1 is D, 2, yeah, exactly. 2 is, I'm sorry, 1 is T, I'm sorry, 2 is D, and then 3 is F. So we know for an F subshell, the L value must be 3. All right, let me just draw a line. So this is for F. What are the possible values for M sub L? Well, it can go from negative L to positive L, right? So -3, -2, -1, 0, 1, 2, 1, again, 2, 3. Okay. So there's 7, how many orbitals are there based on these values for M sub L?
7,
7 orbitals, and each one can hold how many electrons, guys?
2,
2, right? So we have 7 orbitals, each one can hold 2, so maximum of how many electrons can be found in an F subshell? 14, right? 14 electrons. In any F subshell, so that can be in your 4F subshell all the way to your 100F subshell, but we don't see those in real life, right? So answer to this one is D. Okay. Now let's go ahead and let y'all work on number 19. You got an answer, Maria? Don't say it. Don't say it.
It's.
Is it a letter in the alphabet? Okay, you're close then.
Oh, yeah.
No, I didn't really see that on your paper. I thought I saw like an imaginary number as one of the options.
Yeah, I got
I
34.
took the square root of -1, huh?
No, I thought it was I squared. That's what you got.
I swear, interesting.
Oh, my gosh. Oh, my God, Alex.
Oh, yeah,
Dylan, yeah, what's up, bro?
yeah.
I have an answer. Perfect. Wait. Wait. Alex, wait like another 30 seconds, okay? And then you can spam your answer in the chat. Yeah.
So.
Say a little loud. Okay. Do you have an answer? All right, you wanna, are you okay with kind of walking through? Exactly.
Yeah.
Okay, let's go ahead and we're all gonna, focus on her, spotlight it on her. She's gonna go ahead and tell us what she thought.
So the order is N, L, M sub L, and then M sub S. So for the first one, like it looks okay, so you get the last one, M sub S, only positive 1/2 or negative 1/2.
Exactly. M sub S can equal plus 1/2 or minus 1/2, like she just said. And that, in A, M sub S is equal to 0, which makes 0 to us, right?
Yeah.
Okay, what about B?
It's not right because if N is 2, L should be 2.
That's really messed up
Yes, exactly.
right there, because
That's how they-
like you said, the only values for L are what? 0 to 1, right? So it can go from 0 to N minus 1. Perfect. So that's wrong. A is wrong. C's gotta be right. Let's go. Why?
Because, so, yeah, N is good, L is good, but if L is good, M.
What can M, what are the possible values for M sub L for any L?
For any L.
So L is equal to L. What can M sub L equal?
Minus like positive L.
Exactly.
Yeah.
So I'll do this minus L to 0, positive L.
Because the L is 0, M can't be that.
Okay. Yeah, that's where we mess up right there. These gotta be right. Okay, we're getting to the end, but we'll see.
So, E isn't right either for the same reason, because L is 0, so L, M should be. That.
Exactly. So she just said, I'm just gonna repeat it because I'm not sure if they can hear. Because Maria's talking. But I'm just kidding, Maria. But she just said, if L is 0, M sub L can go from negative L to I cannot speak right now, but positive L. So if L is 0, there's only one possible value for M sub L, because you can't have -0, +0, it's just 0, right? So this is, it's wrong there again. By process of elimination, it's E, but tell us why it's valid,
Well, you have an NO2, that means an L of 1 is okay,
okay?
and then a -1, M sub L is totally fine, because L is 1.
Correct.
And then since MS can only be positive 1/2 or negative 1/2, it's 1/2, so.
Exactly, right? It doesn't need to have a plus sign here, okay? That's, I've gotten asked that before, if it doesn't show the plus sign, obviously, it's still a positive number, right? But everyone understand her thought process? Perfect, any questions? No questions? So, no questions, perfect, Michelle, thank you.
So I have a question.
You have a question,
So you know, we said MS can only be positive 1/2 or negative 1/2.
correct?
Why are we choosing the one that's just 1/2?
It could be either, so had it been a negative number here, would that be?
Oh, but it doesn't have any like charge. Can it also have no charge?
I'm sorry, you said charge?
Oh, that's what you were just talking, like her saying if there needs to be like a plus in front of the one.
Yeah.
No, it just means positive, it's not like a charge. Like
Oh,
a
okay.
positive number.
Yeah, like +1/2 is the same thing as just a regular 1/2. It's like, you don't write like +7, you write like 7.
Oh, okay.
Does that make sense?
Yeah.
Awesome. That's what my mom always says. Okay, here's an interesting one. Let's see if y'all memorized your, whatever they are. Oh,
Principles of
Quantum
atomic
mechanics.
mechanic violation things, so.
principles of quantum mechanics. Alex, I just got to this question, man. We kind of cover the answer. Bro, you got like 5 other TVs in here.
That was me, though.
Shadow clones.
Alex.
Okay. Sorry, Alex. Alex, you just feel free to speak up next time when I ask if anyone wants to walk through their train of thought, okay? It'd be nice to hear a Zoomy speak for once. Michelle speaks. Okay. So anyone want to tell me what Pauli's exclusion principle is? Yeah,
So it basically means like in the diagram, you have to fill it out everyone like going up before you can go down.
are you sure?
Maybe getting it confused with another one.
Oh, yeah, never mind. Never
You're
mind.
fine, you're fine. What you're talking about is called Hund's rule, which says that in order, so if you have your 2s and then your 2p, Hund's rule states, if you're gonna fill an orbital, before moving to the next energy level, you have to double it up, right? So 2s goes like that. But if you're gonna fill the 2p subshell, you have to add an electron to each orbital before you start doubling up, because, and that makes sense, right? Because each electron has a negative charge. So would it really be energetically favorable to add 2 electrons into the same orbital when they have 2 neighboring orbitals that are completely empty? It doesn't make sense to do that, right? So what we do is we add it to the next empty orbital, and if we're gonna add another one, we're gonna add it to the next empty orbital before we start doubling up. Like, think about it, if you're staying at a hotel room or a hotel with your family, right? Do you want to start bunking with your siblings when there's a wide open bed next door?
No.
Or you're gonna wait till that bed gets full and then fine, I'll sleep with my siblings,
Yeah.
right?
Wait, who sleeps with them? You sleep with your sibling?
Oh, that's nasty.
Okay. Okay. That was not necessary. That's Hund's rule, okay? Pauli's exclusion principle, anyone know what Pauli's, yeah,
No 2 electrons can have the same quantum numbers, so you need to have one electron spinning in the positive direction and the other in the negative, kind of.
yeah,
Yes, one up, one down.
Yes, they can't have the same address, because that means they're occupying the same spot. Take a negative charge and a negative charge and try to shove them together, that's not gonna work, right? So you always have one up spin, one down spin. So with that, which one is violating Pauli's exclusion principle? A, we all see that, right? And that's because Pauli's exclusion principle is saying no two electrons can have the same quantum number or same quantum address, if that helps you think about it a little bit better. These clearly have the same little address. They're in the 2s subshell, which corresponds to n equals 2, L is equal to 0, M sub L is equal to 0, and they both have upspin, which makes no spin. Makes sense, right? So A is invalid. Okay. Have you all talked about electron configuration?
Yes.
We have Alex. Alex.
All right, I got the next one.
You got the next one? Okay.
I don't think that's so good.
Yeah, what's up?
Can you explain 120 configuration? Are you just like skipping a talk?
Cannot skip orbitals like that. Like the way it's always shown as filling from left to right. Okay, so you always do this like that. You never do this and that, even though you're putting it in a next open,
I was like, let's
you know,
the math to find out.
unoccupied orbital, you're never gonna end up jumping from that C because each of these has a name. So even though this is the 2p, you have the 2px, 2py, and then there are 2pz. So I'm not sure if it's an energy thing. Maybe, probably not, because you would think all these orbitals are relatively similar in energy. But you're always gonna go X, Y, and Z. Alright, X, Y, and Z. You're never gonna go X, Y, Y. I don't know the reasoning behind that, but just know you don't skip orbitals like as seen in B, okay? Good question, huh?
And that doesn't break a rule, right? Does it?
It probably does break a rule, which is why they don't allow it, but I'm not sure. Someone said something.
All right,
Wait,
so
what did
for number question and answer choice here, I understand why it's wrong, but it's something you can actually see in real life, but with all others pointing out. I don't think, right, you would see something like a letter D in an actual like, real life scenario. Because, or wait, I meant to say what? I mean, it's not really right either, right? Because you have to, because Alcott principle states that you have to fill the lowest energy level first before you go into like the other energy levels. So because of that, right? Because the 1s you're filling, like you're half filling it, 2s you're half filling it, you have to fill up the 1s first before you move on. Does that make sense? So you wouldn't really see this at all.
Okay.
All right, question 21. We'll give you all like 2 minutes to solve this.
I have a question though.
Oh, yes.
So when it comes to like transition metals like silver, are we using like the because you know like there's like there's exceptions to like electron configuration. Does it apply to silver?
No, that could be an H with a protruding,
Well, I guess you have to.
I mean, I'll go over them.
it could be an H with a methyl group popping
Why
out.
would there be a method?
You haven't taken Ocam yet. Hey, Rich, can you do me a favor and show me both ways to write the electron configuration? That's how you make them do on the exam 3 review.
Yeah.
For Rutherfordium.
I will, do.
Make sure you do it with silver.
I will.
The whole thing.
Hold it there. Because you got the original way and you got noble gas notation, which is clearly,
So much easier. I love it.
well, just because you always start learning with the normal way before you go into noble gas. So if this is someone's first time seeing it, they need to know both ways.
Right on the electron.
Not too hard.
That's all I know.
All right, raise your hands if y'all have answers. Keep pushing.
Sorry, another professor says that all the time.
Of course I have it.
I didn't answer. Good job, Michelle. Sorry, I just like to applaud my Zoom meetings. They stay looking at the screen this whole time.
And Andy show you, thank you to all my fans for watching the video. Watching love so inspiring and take your time.
Please don't tell me that's. Is that the second one? What is the second one? You just
OG,
wrote?
no?
That OG?
Yes.
Oh my god. That one's like really down low.
You can only remember
No,
a little acronym.
God damn.
that just kind of makes sense of it, like. I can show you what I.
All right, raise your hands if y'all have answers. All right, cool. So we're gonna go through it. All right. So I heard somebody mentioning something about exceptions to the electron configurations. What are y'all, what are the elements that are exceptions?
AG, AU. Gold.
All right, gold is one. What else? Silver is one.
Obsidian. No, obsidian.
Copper.
Yeah. Copper is one. There's one more. Chromium, exactly. So these are your 5 exceptions, stuff I've highlighted in green. Chromium, molybdenum, copper, silver, and gold. Electron configuration, they don't follow your convention.
They used to think.
So first of all, let me write out the full electron configuration for silver. So can you all tell me the electron configuration for silver? Like, I'll write it down, y'all just say it.
One S two, two F, two P six, three S two, three P six, four F two, three D 10, 4 P six. 3 D 9.
All right, great. Now let's write out the noble gas configuration.
A bracket. KR. Rich, is that correct?
No, I'm
Oh, okay,
There's-
okay, never mind.
KR,
5S1 I actually understand that.
5S2, 3. That should say 40, not the.
Pre-med. This is a doctor and clients.
All right, so that is our noble gas configuration. All right, so now y'all have been asking this term, exception. What the heck does it mean? An exception basically means that it doesn't follow your general trend of electron configuration rules. Like if this were to be normal, this would be the correct electron configuration, right? But in this case, right, for these green elements highlighted here, the D subshell being full is more important than the S subshell being. So because of that, right, what it'll actually do is one of the S electrons will move itself to the D orbital. So this will actually be 5s1, 4d10. And in the case of something like chromium, right, where it's let's see, 4s2, 3d4, it's same thing will happen. So one of the S electrons will move over to the D because since Alpha principle, right, the D orbital is higher in energy. We want to make that more stable first. So that's why we'll fill up all the orbitals in the D subshell without really worrying about the S. So it'll be 4s1, 3d5. Now, with that being said, what would be the correct answer to 21? A. So KR 5s1, 4d10. That is exactly correct. Yeah.
So look, so what did they call it? So if we were to be asked like what is the valence electrons, would it be 1 or would it still be 2
The valence electrons for which one? Sorry?
for this element? in
For
question?
silver. So the valence electrons, right? It would actually be 1, right? Because 1s, and then it would be 5 for the D. So 1 plus 5, there's actually 6 valence electrons. Because remember, right, the maximum is 12.
Outer electrons are always the highest. So the highest should think of the highest end.
I thought it was 8.
Wait, the maximum for valence electrons?
Yeah.
No, it's 12.
The valence for the transition metals, the valence is the S. plus-
So think about it this way, right? How many outer electrons does silver have?
How many outer electrons? It has 11.
Outer electrons?
Wait, no.
Look at.
Zero, that's nine.
Or what, silver?
Maybe zero, right? 'Cause- And what, but it's 5s1, so do you want?
One outer electron.
Do y'all remember the charge for silver?
Ag plus one.
It's always a +1, right?
Yeah.
Does this make sense why it's a +1? If you only have one outer electron, or yeah, the highest, okay, so now that we have a 4d10, it's completely filled, it's really stable. The only highest energy electron there is the 5s1. So does it make sense that silver wants to always get rid of its 5s1, which is why it's always a +1 charge, right? It doesn't want to start dipping into the D subshell because it's already like maxed out, it's stable, everything's perfectly the way it should be, right? So that's why silver is always a +1. It's just something that we learned earlier in the semester. You didn't know why, you just kind of memorized why. And now you know. Yeah.
Yeah, so going back to your question on the valence electrons, is because the D subshell, right, is completely. The valence electrons would also be one, because the thing in the outer
Electron.
subshell would be D. Does that make sense?
Yeah.
3s1.
This is the
Copper can be +1 or
So.
+2. I think it's, I want to say it's because you can lose
So,
both
chromium,
of.
The configuration is what, 4s1, so 3D function,
Well,
or it would be a argon.
do you know the answer?
I never.
So that means.
I never said that yet.
C.
I guess you
It's
did
great
listen to
spot about
everything.
Yeah.
So we.
Jump.
There's that-
Yeah, it's fine because that's the maximum of what it has. It doesn't have enough. You have 10. But it just wants one electron in every.
Always.
Yeah,
So-
I'm kind of confused, so what's that exception?
Yeah.
Do you mind showing us how there is 12 valence electrons? Because I still don't get how why we have 12 valence.
So it doesn't have any
electrons.
or.
Okay, so,
It is one.
so let's take a look at it. So, D, well, let's see, it'll have 1s, 2, 2s. So this is the second subshell,
Not gonna go.
and third subshell. So I think is it what period on the periodic table 4, right? So let's put the thing right here. So it's the ends 1, 2, 3.
Oh, boy.
So how many electrons are in this outer subshell? Yeah. How many electrons are in the 4?
R2.
Well, there's also a D subshell, right? Because the electron configuration for zinc is what? Argon for the noble gas configuration. 4s2, 3d, 10, right?
Yeah.
So because of that, how many electrons are in your outer?
Oh, you have to add
Well,
them, so it's 12.
Yeah,
Well,
because technically, right, the S, like, it's kind of weird, but the D electrons in this and the 4s electrons are sort of similar in energy. That's why you add them up, 2 plus 10.
In the same group.
Because you got like 7 S. Obviously, don't have time for another one.
All right, do y'all have any more learning questions at the moment?
no. So in this same aspect of question, so silver will be 11 valence electrons, right?
Exactly.
Yeah, that makes sense. But if the elements were to be like BR, I think, for example, so it would be 7 valence electrons. So,
Exactly. The transition metals are the ones that are like kind
okay, that have to makes sense.
of. All right, Michelle, I'm glad,
Just like
glad to hear that.
regular
you got things done.
configuration, and then you have the
I
noble.
like that. So,
Because you can consider what's in the only applies to information.
Like he did it, like,
For like.
he did it like.
What I have so far is just.
yeah, we were just explaining like the reasoning behind the exception, like why the exception are.
All right.
And the transition.
Go here. Then we're gonna go here. Then we're gonna go here, and then that's gonna be the.
All right, scan the QR code,
Transition.
so you can contribute to statistics.
Yes, you are a part of our statistics.
I'm going to legitimately work on the exam average for this previous exam, right, like right after this. So y'all get those results. P-value? I mean, I'll calculate that. Let's just say we can reject the null hypothesis.
Oh.
That there is no association between students who go to our sessions and students who don't.
Wait, Anderson, bring your-
In any association. for this-
show you. should
Get
go
it from there, everything else.
It's for extra credit.
You just did it wrong.
That's, I know. how-
No, stage.
And then.
So there is an association.
You didn't show, you should.
Oh, here we go. What's this?
Yeah.
Bro, how did you figure that out?
You do your slick.
Bro,
Yeah.
we're gonna- I've been trying. But I love all 30 of
Wow.
them. I know, yes.
I think it is. I want to do that.